Hi everyone. So the topic that we are going to discuss today is acceleration analysis, and it is part of the kinematic analysis that we were performing for all those mechanisms that we have been talking about. So this is going to be an interesting segment because it is built upon the previous segments, and it is going to give you some headway into the force analysis subsequently. So whenever we start a new topic, we ask these two questions. What is that topic and why we are going to study that? Acceleration, for that matter, is going to be defined over here. It is the time rate of change of velocity. But this is actually one part of acceleration which we call the linear acceleration. So this is actually the linear part. There is another part which we call angular acceleration, which is defined as alpha. There's also going to be time rate of change, but that is going to be corresponding to the angular velocity. So obviously you can see that acceleration is going to provide us the information that how the velocity is changing with time, both in terms of linear velocity and the angular velocity. And if we connect this realization with the previous discussion on kinematics, we can recall that we defined kinematics to be explaining or exhibiting motion of one rigid body or multiple rigid bodies, but without considering the forces or torques associated with that movement. And this is only possible if we define position of single body or multiple bodies, if we define the velocity of all those bodies, and if we define the acceleration in most of these cases. So position is actually necessary to find out the velocity because it is the time rate of change of position that defines the velocity. And once we have found out the velocity, it is going to be, after taking the time derivative, provide us the information about the acceleration. So that's why you can see that the discussion that we are going to start discussing today is dependent on our previous discussions that we had corresponding to velocity and position. So all the details that we have already discussed and all the derivations are going to be equally relevant over here. And then we need to see that potentially we can take another time derivative to find out something about the jerk produced during this motion in a single body or in multiple bodies. And if we jump on to the dynamics part, we would still require this kinematics available over there because, for example, the very commonly known expression of force to be equal to mass times the acceleration, you can see that over here we require this acceleration to be there in order to define the force corresponding to that particular body having mass m. So that's why it is important to have the acceleration analysis, because it is going to define how the velocities are changing with time, and on top of that we're going to use that to find out something about the jerk produced during this motion, or potentially if we are doing the dynamic analysis, then how the forces or torques are being generated in this motion. So the next question is how to perform acceleration analysis. Obviously, we have seen in case of position analysis as well as velocity analysis that there are two approaches for doing that. One is what we call graphical approach, and the other one is analytical approach. And in graphical approach, if you can recall, we defined vectors in a frame of reference, and this vector was corresponding to position, and then we used this information of this vectorial representation to find out velocities. And then obviously we're going to make use of these vectorial notations to find out the acceleration. And this was the graphical method. We are going to still use that over here as well. The analytical method was emanated from defining a vector r, for example, which was defined in the Euler notation for vectors form like this, where you have the magnitude over here and you have the angular displacement represented in this notation. And then we took the time derivative, as I've previously mentioned, to find out the velocities and all that. So we're going to make use of this information to compute the acceleration. So both the methods, and graphical as well as analytical methods, are going to be used over here. But in order to achieve the acceleration analysis, we're going to first start from performing the acceleration analysis for single body systems. We will do that first, and then we will move on to multi-body system. So we're going to go in a stepwise fashion over here. So a single body first, drawn graphically. Let's start this process. The very first thing that we generally do is to draw the axis. This is X, this is Y. The body can be assumed to be pivoted over here at this point, label as A. So instantaneously the body may look somewhat in this orientation. The other point that is point of interest for us, because generally we need to connect this link with the other links, so this point is important for us, so let it be labeled as P. The vector which defines point P with respect to A is this. We defined previously as RPA, and obviously it is going to have an angular displacement associated with it, which is defined as theta. So when we move on to the velocity representation over here, we define what generally is the angular velocity associated with this body. And if we define that to be omega in this orientation, because it goes clockwise corresponding to the x and y convention that we have used, so this is going to be the negative sense of omega. And as a result of that, the linear velocity component on this link at point P is going to be somewhat in this orientation, and obviously it is going to make a 90 degrees with the original vector of position. So this is VPA, and when we move on to the acceleration part, obviously you're going to have the angular acceleration associated with this body, and if we define it in this orientation, so this is the positive sense of acceleration. And when we do that, obviously the acceleration is going to be defined as a vector over here. Possibly this may look something like this, which is the acceleration of point P with respect to A. And obviously it is going to have two components. One is the normal component, which we also called centripetal acceleration. This looks somewhat of this form. So this is APA normal. And the other component is going to be the tangential component. This may look something like this. APA tangential. Now obviously graphically we have defined the position as well as velocity as well as acceleration over here. So now the analytical approach. So the position vector that we have defined was RPA, and that can be written like P e raised to power j theta, where P is the magnitude of the vector and theta is the angular displacement. And when we take the time derivative, we're going to find out the velocity of point P with respect to A, and that is going to be d by dt of this whole expression, P e raised to power j theta. And obviously this is going to be equal to P j e raised to power j theta, and then the d by dt of theta itself, which obviously we know that it is equal to the angular velocity that we have drawn already. And now when we take the time derivative once again of this whole expression, we are going to find out the acceleration of point P with respect to A, and that is going to be equal to d by dt of this expression, P j omega e raised to power j theta. And over here, if we can analyze, Pj is constant, it is not changing, so that's why we can take this one out, and this turns out to be this expression. Now over here, obviously you can see that omega is also changing with time, and e raised to power j theta has got the variable structure as well. So that's why we are going to use the product rule over here. So as a result of that, this is going to be equal to Pj, and inside these brackets you're going to have d omega by dt times e raised to power j theta plus omega as it is. Then you have j coming in from this e raised to power j theta, and then you have d by dt of theta itself, which is obviously omega. So as a result of that, you're going to have Pj, d omega by dt is defined as alpha e raised to power j theta over here. Then you have this expression Pj multiplied with this, so this can be plus Pj omega j e raised to power j theta, and then you have omega itself over here. So over here you can see that j is being multiplied with j, which is going to be -1, which is going to change this sign. So as a result of that, this turns out to be P alpha j e raised to power j theta minus P, this j multiplied with j is taken care of, and then you have omega multiplied with omega, so this is going to be omega squared e raised to power j theta. Now you can see that this is the acceleration of point P with respect to A, and if we analyze over here, you can see that this component, because of alpha associated with it, it is the component which we have defined already, the tangential part. So this is a tangential, and this part, because you have omega squared in it, and negative sign is also indicating the sense of direction it is going to possess. So this expression is corresponding to the normal part that we have drawn over here. So this comes from the angular acceleration manifested in the tangential part of the acceleration, and the an comes in because of the centripetal part in it. So over here you can see the windows side by side. the analytical approach, and the graphical approach. And you can obviously make analogies between what is being graphically shown over here with what we have derived in terms of expressions over here. And you can obviously see that the normal component of the acceleration is the same component that we have drawn in the graphical window over there, and the tangential part is illustrated right over here. So in this fashion, you can see that you have both the approaches valid enough to illustrate what is happening with the kinematics of the body under motion. So what if point A is no longer stationary, which means that as we drew this system previously, the point A was just pivoted. You only had the rotary movement possible. But in this particular case, we're assuming that this is no longer the case. So possibly the system may look something like this, that you have some sort of a block which is movable over a flat surface. And the acceleration that we're expecting on this point A is horizontal, and we are labeling this to be AA. Now, we need to draw the axis in this case as well, and let me quickly draw that to be consistent with the previous discussions that we had. Over here we have x-axis, and over here we have the y-axis. Now, this kind of system is very popular in control domain, and possibly you're going to study that in the subsequent courses. That's what we call cart and pendulum system. Actually, in this case, the way we have drawn it, it is the inverted pendulum that we have drawn. So this is a very common system to be controlled in the control paradigm. So you will see that in subsequent discussions. So in order to analyze what is happening at point P in terms of acceleration, we need to draw the acceleration diagram over here. And this diagram is constructed using the similar approach that we have already used in constructing the velocity diagrams. So what we're going to do, we're going to start with the acceleration of point A, once again drawn. So this is AA, and from the head of this vector, I'll try to draw the vector APA, which is acceleration of point P with respect to A. I'll try to draw it using the same color. So this looks somewhat of this shape. So this is acceleration of point P with respect to A. And now using the resultant vector principle, I can draw using a different color the resultant vector, which actually is acceleration of point P when you have a moving point A in your case. So in that scenario, you can see that AP is going to be equal to APA added with the acceleration of point A. So this is the expression that we have got in our hands. And the same expression can be rewritten in terms of finding out the relative acceleration expression, which obviously is going to be acceleration of point P when you subtract the acceleration of point A from it. So we can use these expressions in two different cases when you have the relative acceleration to be found out. or if you wish to find out the difference of acceleration, so that's also possible. So we'll raise another question, that is, what if point P, which is over here, is also changing its length, which means that in our mechanism a specific link length is also changing. In that scenario, we have to revisit the previous definitions. So let's do that. We said that the vector, position vector, is defined to be equal to p e raised to power j theta. And when we took the time derivative of this, we found out the velocity. Let's now once again do that. P e raised to power j theta. Now what we are trying to say is that this link length p is also changing in our scenario. So when it happens, it means that you have to consider the product rule in order to compute the time derivative. So which means that it is going to be equal to p dot e raised to power j theta plus p omega j e raised to power j theta. Now you have two terms over here in terms of velocity. Now when you take the time derivative once again to find out the acceleration, so this turns out to be time derivative of this full expression, p dot e raised to power j theta plus p omega j e raised to power j theta. And when we do that, this would mean that you're going to have one component over here which appears like p double dot e raised to power j theta, and then you're going to have another like p dot omega j e raised to power j theta. So this is the time derivative of this term over here, and then added with the other term, the time derivative of that is going to be equal to for this term you're going to have minus p omega squared e raised to power j theta as one term. You'll get another term like p dot omega j e raised to power j theta. That's going to be one term, and the last term is going to be plus p alpha j e raised to power j theta. And that's because you have this term manifested like this whole term. So with this realization that now you have got quite a few terms in this acceleration expression, and I can obviously see that this term over here, let me box it, and this term over here are the same terms, so I can add them together. So as a result of that, I'll get the cumulated expression to be p double dot e raised to power j theta plus 2 p dot omega j e raised to power j theta, and then you're going to have minus p omega squared e raised to power j theta term, and then you're going to have the last term like p alpha j e raised to power j theta. And if I can identify that, what is the nature of these acceleration terminologies, and they would sound familiar to you. Obviously I can see that there is this term with the P double dot term. This actually is because when the link length is going to change, there is possibility of having a slip in that movement. There's this term that you have seen previously. This term was having omega squared in it, and that was defined to be the term which was normal, or if I may recall it, this was centripetal term. And there is this term which was already there in the previous expression as well. That was the tangential component of it. And this term is a new term. This is generally called Coriolis. And this has got a specific nature of it, because you can see that there is one velocity p dot appearing over here, and the other velocity is the link's angular velocity omega. So when you have two different velocities multiplied together, you are going to have the Coriolis factor in the acceleration as well. So as a result of that, you have got the acceleration expression to be quite elaborated expression, which contains quite a few interesting terminologies in it. You guys must have realized that we have raised a few questions along the way in order to add further depth in the discussion. And in this continuation, we have found out some interesting factors in the acceleration, like slip and Coriolis. And since you now have this expression in front of you, which is much more refined as a result of these questions, I'll raise a few more questions. The first one, like, can you visualize such link or such arrangement? And if you can do that, please do draw it over here in this slide. And if you're going to do that yourself, that would be great. Another question can be that have you experienced Coriolis acceleration yourself? And I'm very much sure that you must have. So can you explore that? And the possible way of exploring it to explore joyrides. So the movement in the joyrides is going to have potentially the Coriolis factors added to it. So can you explore joyrides in order to explore Coriolis acceleration? Another further question to add further depth in the discussion is to explore the effect of jerk in such kind of movements. You took the time derivative of velocity to find out the acceleration, and you can take another time derivative of the acceleration expression to find out that. So I'll ask you to explore this activity as well. So in order to start acceleration analysis for four-bar mechanism, we have to draw the initial sketch once again, and quite obviously we are going to follow the same rituals of defining the axes. This is the x-axis, y-axis, and in order to have the mechanism illustrated, we're going to start from the link number 1, and to follow the convention, generally we said that we're going to have the ground link labeled as link number 1. So you have 2 points which are grounded. So the ground link is going to be like over here, which is labeled as link number 1. Link number 2 is going to be the crank, and we drew it last time like this. Sorry, redraw it. That was something like this. So this was crank, which was making an angle with the horizontal axis, and then you have the coupler link like this, and then the rocker link like this. And obviously, to be consistent with the axis that we have drawn already, we are going to have the same axis convention followed over here. So this is theta 3, this is theta 2, and theta 4 was like over here. And obviously theta 1 is equal to 0 because you have both the pivoted joints. The ground link is perfectly aligned with the horizontal axis. Alright, so with this realization that we have got this 4-bar mechanism drawn once again, where link number 1 is over here, link number 2 is over here, 3 is over here, and 4 is this, we can start our discussion on to the next state, which is we are going to impart the angular velocity omega 2 in this sense, which is the counterclockwise. And as a result of that, all the connected links are going to have movements imparted on them. And obviously these are going to have the angular velocities as well. So this is going to be omega 3 for that matter. Omega 4 is going to be right over here. So this is going to create velocities as a result of imparting input angular velocity on the crank. And obviously in a similar fashion, because we are doing the acceleration analysis, we are going to impart the angular acceleration alpha 2 over here in this sense. And as a result of that, we're going to have the angular acceleration on the coupler link alpha 3 and the angular acceleration on the rocker link alpha 4. And to complete the labels over here, this was also defined as R1, vector R1 in a vectorial form. This was R2, this was R3, and this was R4. And we had another notation over here. This was defined as A, link length A, and link length B over here, link length C, and the ground link was D. And the last thing was that like this point was defined as point A and this was defined as point B. Remember we just said that if we have a link like this and if this is point A and this is point P and this was the point of interest for us, and then we said that if point A is itself moving with a specific acceleration, and in that scenario it was AA over there, and point P moving or having an acceleration with respect to point A was defined in this fashion, APA, and then we said that as a result of that, after drawing the acceleration diagram, we may find the acceleration of point P over here. So making analogies with the 4-bar mechanism, we can say that point B currently is point of interest. This is important for us. And point A is moving similar to the point A moving over here. So as a result of that, the equation that we wrote down for this case, which was AP was equal to AA added with APA, that can be rewritten for this case as well for 4-bar mechanism, and that would be acceleration of point B is equal to acceleration of point A added with acceleration of point B with respect to A. And if I can do a little bit of manipulation, I can say that this is going to be AA added with ABA minus AB to be equal to 0. So let me label this equation as equation A, and I'm going to use this equation subsequently. So now we will start from vector loop equations. So using vector loop equation, we can see that R2 plus R3 minus R4 minus R1 is equal to 0. It means that this R2 added with this R3, you reach to the same point B when you add R1 with R4. So if we use the notation that we have been using previously, we will say that this R2 is equal to A e raised to power j theta 2 plus B e raised to power j theta 3, which is R3, minus C e raised to power j theta 4 minus D e raised to power j theta 1, which is actually equal to 0. So this is this equation, and if we differentiate it to find the velocity, the vector loop equation for that, we're going to find out that this turns out to be j a omega 2 e raised to power j theta 2 plus j b omega 3 e raised to power j theta 3 minus j c omega 4 e raised to power j theta 4. And since theta 1 is equal to 0, so you don't have that term appearing over here. So this turns out to be equal to 0. And if we once again differentiate it with time to find the acceleration equation, this turns out to be minus a omega 2 squared e raised to power j theta 2. And actually you're going to have two terms in it, because you have omega 2 varying with time and theta 2 also varying with time. So that turns out to be and we have done it already. So this is a alpha 2 j e raised to power j theta 2. So this corresponds to the very first term over here, differentiated once again. Then you have added with another set of terms, which is minus b omega 3 squared e raised to power j theta 3 plus b alpha j e raised to power j theta 3. And then you have with a minus term minus c omega 4 squared e raised to power j theta 4 plus similarly c alpha 4, and I should write alpha 3 over here, alpha 4 j e raised to power j theta 4. So this is equal to 0. Now I'll ask you to label this equation as equation B, for example, and we're going to compare the two equations that we have listed, A and B, together. Now you can compare the two equations, A and B. You can see that over here you have AA, which is the acceleration of point A on the diagram. This corresponds to these two expressions. Similarly, ABA, which is acceleration of point B with respect to point A, and that corresponds to these two expressions. And similarly, AB is listed right over here. And this is with a negative sign, and I can see that a negative sign is appearing over here. So in this set of expressions, you can see the first one is with omega 2 squared term in it. And if you recall, we said this component to be the normal component with a superscript n associated with it. So this is a n normal. And the other one is the tangential component, obviously. So this is a tangential. And similarly, for these expressions, you can say that this is a b a normal, and this component is a b a tangential. And similarly, over here, you have this component to be a b normal, and this to be a b tangential. So you can see that the vector loop equation has given you the same expression A, but now with clear distinction that it has got two components. The first one is the normal component, which is the centripetal part of it, and the other one is the tangential component, which is going to be 90 degrees rotated from the normal component. So in this fashion, you can have the two expressions correlated. Obviously, on expression B, we can see that A, B, and C are the link lengths. So we already know these. Omega 2, if I see that appearing over here, has been computed already in velocity analysis. Similarly, omega 3 is known already there, and this is also available. Now we are left with alpha 2, and this alpha 2 is actually the input given to the mechanism. So when this is an input, it means that we know it, or we have control over how the angular acceleration is provided to the four-bar mechanism. So this is under our control. So we can control it. So that's not an issue over here. But what is not known is this alpha 3. So I'm going to place a question mark over here. And this alpha 4, which is also not known. So we need expressions for alpha 3 and alpha 4. So that's the quest that we're going to pursue on the subsequent slides. So we already know that Euler expression said that a e raised to power j theta can be written like a cos of theta plus j sine of theta. So we are going to use this equation over here in order to further expand expression B. So let's quickly do that. So this turns out to be minus a omega 2 squared cos of theta 2 minus a omega 2 squared j sine of theta 2 plus a alpha 2 j cos of theta 2, and since j is already there, so j multiplied with j is going to be minus a alpha 2 sine of theta 2. So this is this first set of expressions added with another set, which is minus b omega 3 squared erase, sorry, let me erase it. This is going to be cos of theta 3 minus b omega 3 squared j sine of theta 3 plus b alpha 3 j cos of theta 3 minus b alpha 3 sine of theta 3 minus, you have this term, so this is going to be minus c omega 4 squared cos of theta 4 minus c omega 4 squared j sine of theta 4 plus c alpha 4 j cos of theta 4 minus c alpha 4 sine of theta 4 to be equal to 0. And obviously I can see that there are real and imaginary parts in these equations, and if I can make you see that over here, this red block is giving you all the terminologies with J in it, which is making it the imaginary part of it. So this J is indicating that, and the other terms over here, let me use a green box over here. These set of values and these over here on that side combined together are giving you the real part of it. So this is real part and this is imaginary part. So when we use these two real and imaginary components separately, we can write down two equations, and since we know that alpha 3 and alpha 4 are the two variables to be known, so two equations and two unknowns are going to work fine. So quickly separating the two, we can say that two components can be that is real and imaginary. When written separately, these are going to be two equations. So the very first one is going to be minus a alpha 2 sine of theta 2 minus a omega 2 squared cos of theta 2 minus b alpha 3 sine of theta 3 minus b omega 3 squared cos of theta 3 and minus c alpha 4 sine of theta 4 minus c omega 4 squared cos of theta 4. So this is equation number 1. And similarly, you can find out components corresponding to the imaginary part, which is going to be alpha 2 cos of theta 2 minus a omega 2 squared sine of theta 2 plus b alpha 3 cos of theta 3 minus b omega 3 squared sine of theta 3 minus c alpha 4 cos of theta 4 plus c omega 4 squared sine of theta 4 to be equal to 0. So this is equation number 2. So we're going to use equations 1 and 2 simultaneously to find expressions. And this turns out to be like alpha 3 is going to be equal to CD minus AF over AE minus BD. And bear with me, I'm going to write down the expressions for C, D, A, and F and all that. Similarly, alpha 4 is going to be in a similar fashion equal to CE minus BF over AE minus BD, where A is going to be equal to C sine of theta 4, B is going to be equal to B sine of theta 3, and then you have C, a bit long expression, which is going to be A alpha 2 sine of theta 2 plus A omega 2 squared cos of theta 2 plus B omega 3 squared cos of theta 3 minus C omega 4 squared cos of theta 4. And then you have D to be equal to C cos of theta 4, and then you have E to be equal to B cos of theta 3, and then you have a longer expression for F, which is equal to A alpha 2 cos of theta 2 minus A omega 2 squared sine of theta 2. Then you have minus B omega 3 squared sine of theta 3, and then you have plus C omega 4 squared sine of theta 4. Now you can obviously see that you're going to plug in these values over here in these expressions for alpha 3 and alpha 4. And obviously you can also register that among all these expressions over here there is nothing which is currently unknown. Obviously, because you're performing the acceleration analysis, you are going to find out the velocity values from the velocity analysis and thetas from the position analysis. Obviously you're going to use those, but once those have been already computed, you can plug those values in over here in order to find out alpha 3 and alpha 4, and eventually these are going to be plugged in expression A. And if you recall, in the expression A there were three subcomponents. There was acceleration of point A that was given, there was acceleration of point B in relation to the point A, and then you have acceleration of point B indicated over there. And obviously in both of these, in all of these expressions, you're going to have the normal component and the tangential component added in it. So you can plug in these alpha 3, alpha 4 values in equation A in order to find out what is happening at point A in terms of acceleration, what is happening at point B, and what is happening at point B with respect to A. So all these accelerations can be computed, which is going to give you the deeper sense of how the acceleration is taking effect. And when you compute the acceleration components and all the constituent components, the tangential and the normal components, the diagram is going to have this shape as indicated in subdiagram A. And when you draw the acceleration diagram on similar grounds that we have done in the class as well for the velocity diagram, that's going to be this shape. So this gives you this realization that the acceleration of point B, which is point of interest for us, is going to be computed by having the acceleration of point A computed and then the relational acceleration of point B with respect to A computed as well. So once you plug in all those values and plug those values right there in those expressions, eventually you're going to get all these vectors properly computed. So on your notebooks, you have to counter check the work that we have done today. So that's absolutely necessary that you do it yourself once again in order to have the assurance that whatever we have presented today is correct and according to how it should be. And then you have to do the similar exercise for the 4-bar slider crank mechanism. We have done it for the 4-bar pin jointed mechanism today. You'll need to do a similar exercise for 4-bar slider crank mechanism. And as we have done previously in the velocity analysis or position analysis to find the kinematics of any point on a linkage, so over here you have to do it for the acceleration as well, and that's the section 7.5 that you have to do it. And the last point, which is very important, and we have said it previously as well, but now I need to reiterate that it is absolutely necessary that you practice the end chapter problems or the examples so that you develop a deeper sense of kinematic understanding of all these mechanisms. So this is going to be absolutely necessary for you to practice hard and all those problems done yourself on your notebooks. So having said that, this is it for the kinematic analysis, and we have covered in quite a lot of detail all these methods of kinematic analysis of mechanisms, and I hope that now we are ready to shift on to the other stages where we are going to study the cam follower mechanisms and the geared mechanisms in much more detail. So that is going to be the discussion started from the next chapter. So this is it for today. Thank you very much. And if you have any questions, we're going to have the question and answer session just adjacent to this discussion, so we can obviously discuss all those issues over there. So if you guys have got any questions, you can discuss it in the comment section, or you can just have the question and answer session scheduled with me. Thank you.